Hi, everybody. My name is Michelle Smansky. I am the undergraduate academic advisor for Material Science and Engineering. We are going to do some lab demos tonight and give a lab tour. We are going to be watching some videos and some lab demos that some of our seniors put together for us. These are exciting demos that we're going to be watching. Also, we're going to watch a tour of the labs. And in the tour, you'll see Luke is describing each machine and what it's used for and the hands-on experience that they have gotten from it. We are going to be watching the first video, then we'll pause and answer a few questions, and then we have one other video to watch. They're about 10 minutes, but they're very informative, very useful, and we hope that you enjoy them very much. So I am going to get started here.
Hello everyone, my name is Luke Bradshaw and I'm a senior in Material Science Engineering at Tech. I wanted to talk to you today about ceramics, which is one of the categories of material that we work with. Ceramics are generally hard, brittle materials. They have general good heat resistance and corrosion resistance, and they're generally made up of mixed ionic and covalent bonding, but there's also a type called polar covalent bonding. What that means is that there's more charges on one side of the crystal lattice than the other, so if you change its shape, you can make a potential from one side to the other, which is a voltage, and you can use that to power lights or speakers or any other kind of thing. So we have one set up here. What's going on is we have our leads coming off of this guy, who's our little piece of piezoelectric film. So if I bend this, one side is undergoing compression and the other side is undergoing tension. And you can see on the voltmeter it jump up and down as I do that. And that can also be used to power lights. So I'll take you guys in the other room and we'll turn out the lights and I'll show you that you can actually generate light with just movement using piezoelectrics. Yeah. So here are two piezoelectric circuits that I showed you out in the other room. Same setup and everything, but now I'm going to turn off the lights and you'll be able to see it light up. So just look at this LED here. It's a faint red glow. And then here's the other one, which generates much more voltage. So there's a lot of cool applications for piezoelectrics. Some of the most common ones are energy recovery methods of ways to take mechanical movement and turn that back into electrical energy. Some of the other more interesting ones is articulating movement on a very small scale. So if you want to move an object, let's say 2 or 3 atoms over, of a couple nanometers, you're not going to be able to do that using any sort of movement system that we normally use, like screws or pushing or measuring how far it's going. So what you actually do is you take a piezoelectric and instead of squishing it to get a voltage, you run a voltage through it, which changes its shape. And that way you can dial in the voltage and get very exact fine movements, which they use for atomic force microscopes and other types of technology like that.
Hi, so I am Kendall. I am a junior at Virginia Tech studying material science and engineering. And these examples in front of you are some of the examples of ceramic materials in everyday life. So what we have here, this is a ceramic paint scraper right here. And you can see the end right here is made out of a very tough ceramic, so it makes it easy for the paint to be scraped off of, let's say, a wall or something like that, which you're trying to get rid of. The next example here is a ceramic film. If you can see that right here, this is used for filtration, and so we have, let's say, molten metal is coming through. And what this ceramic foam does is it filters out different sort of particles that we want to get out. And so that basically we use, let's say, molten metal, pure molten metal right here. And so this third example right here, this is a catalytic converter. And what we see here, this is made out of a ceramic, and it filters out different gas particles via a redox reaction, a reduction-oxidation reaction. And what happens is, let's say gas particles are coming through, and let's say a car engine, and so the gas particles filter through, and it processes this reaction, and what is left is it makes the gas less toxic. So these are just 3 examples of what ceramic is used for in your daily life.
Hello, my name is Thomas Canfield. I am a senior in materials science and engineering here at Virginia Tech. And so here I'm going to be doing a demo with a nickel and titanium alloy, which has been coined as a shape memory material. And as I will demonstrate, this is because when you look at this material, we're going to stretch this spring. And as we stretch this spring, it's currently in its martensite phase at a cooler temperature. But once we add heat, the phase is going to then change its crystal structure into the austenite form, which will then cause it to bend away, as you can see there. And then once again, in this material, it's the same principle of a phase change and change in the crystal structure given the heat. So we're going to coil this up and drop it into some hot water, and it'll straighten out this material. And as you can see, it's nice. Once again, this is a nickel titanium alloy. It's a shape memory material, and this technology is also commonly found in braces. So they use this to straighten out your teeth. So the increase in temperature in your mouth heats up the spring and causes your teeth to straighten out, as so.
Hey everyone, so another one of the really cool opportunities we have at Tech here is the opportunity to work with the foundry. We have a pretty large scale, medium scale metal processing and casting department. It's run by Dr. Druschitz, and these are some of the things that were made. This is a hooky bird. That was actually a investment cast was made, and then it was cast out of, I believe, steel. And then it was painted, covered with an enamel to protect it. And then here are 2 more examples of cast pieces. What I wanted to talk about here is these 2 pieces are approximately the same age, but one of them was covered in a protective enamel and the other one was not. And you can clearly see that the one that was not covered is starting to corrode at a much faster rate than the one that was protected, which is why we use this sort of protective coatings on metals, is to keep them going. The last cool metal thing I have here, something we do a lot as materials engineers is we look at failure, how materials behave when they're put under different forces and how and why they fail. So one of the most classic examples we do is just tensile testing. So we take this bar and we machine it out so the middle is thinner than the outside pieces, which are where it's held. That ensures that it will fail somewhere in this thinner area. We then pull on it until it eventually snaps, and then we can look at the surface of how it broke and understand things about the microstructure of the metal and how it behaves under force. This is very useful, and this is not only done for metals, but we also do this for polymers and different composites, just trying to test them in different loading conditions and see when and why, more importantly, that they fail.
Hi everybody, I'm Tim Brewer. I'm currently a senior in material science and engineering, and I'm going to show you a little bit about how superconductors work in magnetic fields. So, as you can see here, we have a magnet, which I'm holding in the tweezers, and a superconductor, which is here in the pan. And as you would expect, under current conditions, when you place the magnet on top of the superconductor, nothing happens. So now we're going to cool the superconducting material. We're going to do that with liquid nitrogen. We're just going to surround the material with this cold substance, and that's going to chill it. So as you can see here, we have the magnet actually hovering over the superconducting material itself. As you can see, the magnet is suspended in air. It bounces and it's not held up by anything except the interaction of the magnetic field of the magnet and the superconducting material itself.
Another cool effect with liquid nitrogen is something called the Lindenfrost effect. And liquid nitrogen is very cold. If it's conducted your skin for a long time, it can hurt you. But if you just pour it on top of your skin, it just rolls off immediately. So what's happening there is as soon as the liquid nitrogen contacts your skin, it vaporizes, turns into a gas, and that layer of nitrogen gas actually protects you and acts as an insulator between you and the super cold liquid nitrogen. That way it can just roll off your hand. The same effect can also be observed when you see people wet their hand and touch molten metals and they don't get burned. It's that same thing. That layer of gas that forms immediately acts as an insulation barrier and actually protects you from the thermal effects of either cold or hot. So another cool demo of metals is the example of something called screening tin. So tin, when it crystallizes or solidifies from a melted stage, it actually starts twinning. So what twinning is means that two crystals share the same lattice point and can grow over each other. So the result of that is that when you put dislocations through the material, it actually shears off those twinned crystal lattices, and you can hear the sound when you bend tin. It sounds like a crackling, kind of high-pitched popping sound. But I'll put it next to the phone and see if you can hear it. It's pretty cool stuff. So tin actually isn't the only metal that does this. Also, gallium does this, indium does this, and I think one or two others. It's just a result of the crystal structure of this type of metal.
Hi, my name is Anna. I'm a senior here at Virginia Tech in Material Science and Engineering, and one of the things I'm going to be telling you about today are our design teams within this department and the conferences we get to go to. So every year we go to this really big conference in the fall. It's called MS&T, which stands for Material Science and Technology, and we bring 3 different design teams to compete. One of them is the dome team. So each year we design a different dome, and we bring it and we compete against other schools, and essentially they place it under this really big hydraulic press and push down on it as hard as they can, and the team that handles the most pressure wins. So these 2 actually maxed out the machine and took as much force as possible, and this one actually broke the machine, so no other teams could really test anything after us. But this one is really, really fun. It's super energetic, and all the schools are competing against each other. And then we have 2 other teams that are ceramic and glass based. So one is called the ceramic disc team, and this is one disc that was entered in the aesthetic competition. So every year you can enter the aesthetic competition or the throwing competition, or both. So you have to make a disc that's made of a ceramic or a glass that fits into certain parameters that are set by the judges. And then everybody goes, and for the aesthetic competition you just lay them out and the judges judge them against each other. And then for the throwing competition, each team sends out one member to actually throw the ceramic disc into a disc golf net, and whoever's takes the longest to break, like you step back a distance every time you throw, and whoever throws it the longest without breaking wins the competition. So when I went, we actually won that one too. It's super awesome. There's like bleachers full of students, everybody is cheering, and it's really, really fun, and you actually get a cash prize too, so that's not bad. You get a cash prize with these ones too. And then the third competition is ceramic and glass as well. It's a mug drop competition. So essentially it's similar to the disc competition, but it's just dropping a mug from varying heights off a ladder. So again, bleachers full of students, everybody submits a mug to the competition, and the way that you win is that after each drop they test your mug to make sure it can still hold water, and if it does, then you get to move on to the next round, because a mug doesn't function if it can't hold any liquid. So whoever's can get dropped from the highest height without breaking and essentially not being able to hold water wins. That one's really fun, super high energy, and it's a really great opportunity not only to compete against all of these other schools, but also to network with them. I met a bunch of professors and students from schools like Clemson and Penn State, and just kind of networking in the material science community is a really, really awesome opportunity, even though we're competing against all of them.
I'm going to make Luke a panelist. Luke was our producer for the video. He made the video with the classmates and was in charge of everything. So if you guys have any questions about those examples and those demos that you saw, please ask, and Luke will respond right away. And I think you have some samples to show them right now, don't you?
I do. I have sort of repeats of the same samples, but if anyone had a specific question. Okay, so how many people per team, Sophia? So the team, it depends basically per submission. You need at least one person. So a single person can't do 2 entries, but normally there's about 2 or 3 people per question, or sorry, 2 or 3 people per category. and we generally enter like multiple groups, and then we try and send at least one person per team. Generally, it's the person that was the most involved, but a lot of times we have enough space that we can actually send everyone to the competition and the conference, which is really fun because a lot of the fun of the conference is not just the competitions, but it's the networking and getting to sit through all of these presentations by people that are very, very good experts in their field, and they have all very cool stuff to share with you. Sometimes as an undergraduate, it can be a little bit over your head, but it's still enlightening to like sit through them and understand what people that are at the cutting edge of those fields are working on.
Look, that aesthetic disc that Anna held up, the glass one, was that yours?
Yes, that was mine. So for that, we were trying to look at a way that we could do some sort of glass work, and we were able to find a local glass blower who lives just over the hill in Giles County, about 10 minutes away, and he was able to work with me to make those. And the deal was that I had to work for him for about 3 hours per hour that I would get of him working with me. And so he would just have me do very simple things like these things called pungies, which is the sticks that you have the glass attached to. And so my job was just to roll them and keep them hot. And then he would take them and do his fancy work. And then after doing a couple hours of that, he would sit down with me and work on my creations.
I do want to elaborate a little bit on the shape memory alloy. One of the one use that they're looking at for that shape memory alloy now is to help people with seizures. So they would take a small piece of that material and implant it in the brain where you're having the seizure activity, and that metal would respond to the seizure, stopping it. So that shape memory alloy has many applications, from medical use to eyeglasses. Many people have their eyeglasses made of those frames, and I don't want to say unbreakable, but they are very durable. So if you were to sit on your glasses and bend them, you just either apply heat or cold, and it goes back to its original shape.
Yeah, and just to tail on to that, in one of the classes we take here as part of the MSE lineup, we take a class on metallurgy, and they always have the demonstration of those glasses. And ideally, the temperature that the shape memory alloy corrects at and goes back to its original state is below room temperature. So as soon as you bend it, it's trying to go back. But there's definitely been you can bend them too hard to the point that you cause a fracture. And then once there's a fracture, it won't go back.
Mm-hmm. We do have a question. Do ceramic majors usually lead to any sort of career in jet engine design? Yes. Go ahead, Luke.
Yeah, so I would say for that, jet engine design is something that is not done by a single person. It's definitely a team of individuals working on it, and you need material science and excuse me 1 second.
Sorry, guys. We just lost power in our building. Luke is in the other room, and I'm here in my office. And oddly enough, the building went out. But fortunately, I'm running on battery.
Okay, cool deal. Sorry if I look ghostly here. I promise I won't tell you any more any scary stories while I'm set up like this. So yeah, back to the question. You definitely need material science engineers to work on designing the materials. As far as the mechanics and how they go together, that might be more mechanical engineers, how the flow and setup of the engine is designed. But as far as getting the materials and testing them, that's jobs that is definitely done by materials engineers. So a lot of times, like ME majors will work with material science. Material science does the job of testing the materials, making sure it has no flaws, making sure it obeys creep and can operate in the temperatures that the engine is designed to operate in. So we're definitely combined in that. But again, I would say that you would be able to get into cool design of materials which would be used in jet engines.
Mm-hmm. Ceramics are also used, as many people know, in brakes and other areas. So it made for some interesting sound.
Hey everyone, so this is one of our sample prep rooms. There's a lot of machines in here that we use to get samples ready for different types of analysis. One of the most common is going to be these grinders and polishers. We use this to basically smooth a surface of our sample and get it very flat. This is important when you're doing things like hardness testing, because you need a flat surface. Also things like microscopy, because you need to be able to smooth the surface and then potentially etch it to see grain boundaries and different types of things. Another thing that's important for is if you're doing electron backscattered diffraction, things like that, where you need to have a very reflective, smooth surface to capture what's coming off of your sample for analysis. Some of the other things we have here is we have these presses, which basically allow you to set samples into a polymer puck, and that can be useful for a number of reasons. One of the reasons is so you can use auto polishers to polish it instead of doing it by hand. The auto polishers we have are here and here. You can set them to a certain speed and time, and then literally just walk away from your sample, and it'll continue polishing at whatever grit you had put in there. Some of the other things that we have here in addition to scales is larger grinders. This is grinders and cutting wheels. This is for getting your samples down to size when they're much larger and you need to get them to a workable sample size. And then this is another example of a cutter when you're dealing with hardened materials. This is a low-speed saw, and it usually uses a diamond grit blade. And this is for cutting through samples that are very hard and also making very fine, small cuts. Moving on, we're going into, this is the microscopy and team project room. So people a lot of times doing senior design and undergraduate research, they'll store their projects here. So anytime you come through here, you got to be careful because there's a lot of times a lot of people's different work is going to be at different stages and you don't want to mess anything up. Also in this room, we have all of our microscopes. This is for different types of optical microscopy. This gives you insight into the grain structure and microstructure of the material that you're working with, which has a lot of impacts on its mechanical properties. So understanding the microstructure of the material is key to understanding how the material will behave in different situations. Generally to do this, we polish it smooth, and then you can either use polarized light to look at it, and a lot of times we'll do etching. So what etching does is you put something on there that actually attacks, like an acid, that actually attacks the grain boundaries of the material. So that gets eaten away more, and then you can see the grains individually standing out. That's important if you're trying to do something with grain size measurement or calculation where you need to know more about the grain distribution.
Hi everybody, this is our furnace room for the MSE department. As you can see here, first when we walk in, we have tube furnaces. These furnaces go up to a very high temperature, but you can only heat an object with a very small volume, so there's some give and take there. As we move farther into the room, we have several standard furnaces. They open from the front here, and they have a pretty large volume, so you can create and heat treat pretty large samples. Okay, moving along, we have a very large drop furnace here. So what this does is the bottom comes out with hydraulics, and you can place very big samples here. We use this for melting glass sometimes. Here we have smaller versions of the same kind of furnace, and then several more small box furnaces throughout the room. We have some over here, and then a fume hood as well. And then it should be noted that some of these furnaces can heat treat samples in an inert atmosphere, so you can pump gases like argon and nitrogen into them so that while you're heating metals up, they won't react with the atmosphere and rust.
Hi, this is our processing and mechanical lab. We have a number of different things here. I'll kind of start and then just take you on and on. So one thing here that we have is something called a hardness testing machine. This basically measures how much force it takes to displace a certain amount of material, and that tells you how hard the material is, which is a very important property to understand when you're dealing with different things. There's also a couple different types. So this is Vickers, which is the most common, and then we also have Rockwell hardness testers. And there's a number of types of ways to test hardness. Each of them has advantages for certain materials that you're working with. So the next thing is we basically have, this is called a SIP machine, and it basically uses extremely high pressure. Like you can see on this gauge here, we go up to 70,000 psi if we need, and it's basically you take a ceramic powders or powders of different things and you put them in here, and then you crank up the pressure, and that compresses them together and basically forms what's called a green body, which is a highly compressed version that hasn't been sintered and like atomically bonded yet. here we have, this is actually a corrosion lab setup. This was designed by one of our senior design teams studying the effect of corrosion and different types of corrosion that involve like corrosive liquids or just materials, the liquid materials eroding away, pipes and all that. This is obviously very important for Navy, anyone that deals with like ships and seawater, figuring out why and how stuff corrodes so we can design it such that they don't corrode as fast. So the next things back here that I'll introduce is we have this. This is basically our oven. So anytime you make, and if we're making molds for casting or anything like gypsum molds, we have to heat it up such that we drive all the water out, because you don't want to take something that has water in it and put it in a furnace that's hundreds of degrees, because the water will boil and crack your mold. So this is basically how we can heat it up to about 100 degrees Celsius in that area and drive all the water out before we end up putting it in a furnace that's going to be much hotter. Down here are a mix of all different types of powders. This is for making different sorts of ceramics and different sorts of molds for pouring metal into. What powders you use depends on the application of what you're going to be pouring and using, but they each have their own advantages. This is a really cool thing. So this is actually a ceramic 3D printer. It's a type of an inkjet printer, and it uses stereolithography. So basically what it does is it lays down a bed of powder, and it prints out a 2D pattern of adhesive, a polymer adhesive, and that binds together that layer in whatever shape they have. Then next they scrape over another layer of powder, and the same thing draws the next layer, and layer by layer it builds this thing up, gluing together this ceramic powder. So when you're done, you lift out your sample, shake out all the stuff that hasn't been glued together, and then you would put it in a sintering oven like we saw in the thermal labs. And in the sintering oven you would actually pyrolyze or burn out all of the polymer binder that's in there, and then sinter the ceramic particles together, which will give you something that's actually what we would think of as a hard finished ceramic. Finally, some other stuff for processing here is we have obviously a number of like presses and plates for a similar thing for pressing together powders or chips of different material to get grain bodies that then you could sinter or deal with. Another thing we have here that's important is called ball mills. So basically what ball mills are is you put in your material with these different little ceramic beads, and you put that into a container here that then just rolls. So those ceramic beads are bouncing around with your powder, and as they're falling against each other, the beads will hit one another, and any of your powder between those two beads gets crushed. So it's a way to make your powder finer and to get a more uniform distribution of particle size with whatever type of powder you're working with. And again, the reason we have different size beads is because they have different effects on what you're looking for as far as your final powder. So another cool thing in here is actually these foam cutters that are basically a heated piece of wire. So when you're making something called investment casting for casting metals, you basically make the structure out of a foam or a wax that you want your final cast object to be, and then you build a plaster mold around that, and then you can burn out the inside piece of foam or wax or whatever it is, and then cast into that opening, and the opening will be the shape that you came up with. So one way we use that is we take this foam cutter, and you can cut off, whatever shape of foam you want, and then you glue those pieces of foam together to build your shape. You pour in your plaster mold around that, which hardens, and then you burn out the foam that's on the inside, which then allows you to pour metal into that cavity and get the desired shape.
Hi everyone, welcome to the Thermal Analysis Lab. I'm going to be giving you a tour today. So the first thing we have here is this is the DMA, which stands for Dynamic Mechanical Analysis. So this is typically for the characterization of mechanical properties of, mainly in this case, polymers, just because it's on a smaller scale. And as you can see on this chart, we do different types of mechanical testing, 3-point bend test, tension, compression, shearing. Then moving on to the next device we have here. This is a vacuum oven, so this can pull vacuum and heat your sample at the same time. Then we move to the TGA. This stands for thermogravimetric analysis. So this tells us at what temperature materials degrade, and this can kind of show us how much water and what the material is made of. Moving on to the next device here, we have DSC, differential scanning calorimeter. So this kind of tells us the crystal temperature and how the structure of the material is and how it reacts to cooling and heating within the crystal structure and its phase transformations. Next, we have a particle size analyzer. These are typically used for ceramic particles. This is to make sure they're in the right size that we need for characterization. This helps us kind of characterize and identify the size of the material, which we need to often check against what we receive just for consistency in the bettering of the product. Next, we move over to hygrometers, which measures density, typically used for ceramics. This measures the density of the ceramics. This is a basic scale we use to measure out samples. And then the last thing we have is all over here, and it is a regular tensile testing machine, and this is typically used for more of our metals and ceramics. And that's kind of all we have in the lab. Have some air, liquid nitrogen, and a few other things.
Alrighty, everybody. So, what questions do you have? Let's see. There is a question.
Yes, I can take this one.
Please do.
So, what more input on failure analysis and the importance of that, or specifically what we do for failure analysis? You can clarify that in the chat. Otherwise, I'll just kind of talk about both. So, failure analysis is basically we put stuff under loading and then push it until we force it to fail, and that way we can sort of predict the mechanics that are causing it to fail, and that gives us that gives us a better idea of what's causing it to fail. But that way we can engineer the material so it doesn't undergo those same conditions in the same way that caused it to fail. So let me think of a good example of this. So when you're doing stuff, if you have a material that undergoes, let's say it's a building piece, and it's going to undergo loading, and it's going to be a structural piece. So if it were to fail, it could cause a catastrophic failure. At that point, you would want to make sure that the material you're building with is going to fail ductily, which means that prior to it failing completely, prior to it having catastrophic failure, that it starts to undergo some sort of change. Like it'll elongate. When you think of like bending something that's metal and it like bends smoothly versus if you bend something that's brittle, it just snaps. You want to make sure that the building materials you're using are going to fail ductily, so you don't end up with catastrophic failure. So you would have signs that you're starting to fail before you actually end up with catastrophic failure, which is kind of irreversible.
These labs are the required labs for MSE. Yes, our students have required labs. So lab 1 is during their spring semester, typically, and then you would take lab 2 during your junior fall, and then there is an entire lab dedicated to breaking things, mechanical behavior of materials. Everybody loves that lab. I love that lab, and I've never had it. So you purposely break something and then look at how and why it broke. And if you're going to rebuild it, how do you rebuild it so it doesn't break? Going back to the example that Luke just gave us. So those are 3 of the labs. And then our seniors do a capstone project their entire senior year, fall and spring semester, working to answer a question, a research question, or analyzing something. Luke, tell us about your senior design.
So my senior design has to do with 3D printing of metals using something called additive friction stir deposition. So basically, our goal is recycled aluminum material that's shipped up into very small pieces, and then use this technology of 3D additive manufacturing for metals to basically print that recycled material into a brand new material. And then once we print it, we do stuff like heat treatments as well as optical microscopy and hardness testing and stuff to see how close we're getting back to the benchmarks of a normal pre-recycled material. And this could obviously be very important, the idea of closed loop systems, where instead of having a material that gets thrown away and then has to be mixed with new virgin material and then cast again, what if we could just take all that thrown away material without extra processing and just print it back into new shapes? In addition to that, I'm sure you guys are familiar with additive manufacturing has a lot of unique benefits. One of the benefits is called near net shape manufacturing. So normally if you're making a complex piece like let's say an engine block or something that has large hollow chambers in it, you're going to have to you're going to cast it, and then you're going to have to take something and mill out all of the openings in there, which means that at best, most of your material got wasted because it got turned from a solid block into hollow spaces. But with additive manufacturing, you can print it such that it's pretty close to the shape that it's supposed to be and has those hollow geometries built into it. That way, when you go and mill it out, you're only taking off a couple % of your material, and you're not wasting all the energy of casting those large chunks that you then were going to mill out into empty space anyway.
Thank you, Luke. We have another question, and this might be good for both of us to answer, perhaps. How often do you work on failure analysis compared to making materials? That is going to depend on where you go to work. Right? If you go to work for NASA, you're making materials. You're also making sure that materials you make don't fail. Right? If you go work for Boeing and you're working on a new brake system, you're working to make sure it doesn't fail. So there's always a little bit of failure analysis in the things that you do. There are some people who specialize in failure analysis, and there's others who specialize in making new materials. Luke, why don't you elaborate, please?
Yeah, so I would say that this kind of goes back to what the question had to do with the jet turbine. So a lot of times with any industrial scale project, it's not a single person team. So you're going to have people that are specialized in making sure the material meets all of its qualifications, aka failure analysis, and you're going to also have people that are specialized in actually creating and synthesizing the material that you're going to be using. So you definitely do both. It depends on what you go into. As far as research, you get like when you do research, it's really fun because you kind of get to do like both sides of it. So not only are you designing the material, but you also need to test the material, because if you don't test it, you don't know if what you design is actually what you say it is. So I would say that you definitely get to do both, but there are, as Michelle mentioned, there are definitely specific projects that have to do explicitly with just testing, where you're not actually designing the material, you're just testing it in different ways and looking at how it fails and drawing conclusions based on that information. Whereas other people who are working with, let's say, novel materials and mixtures, like alloys and stuff that really haven't been studied, your whole goal is just to make the material. You're going to do some preliminary testing, but the real science you're doing there is coming up with formulation for the material, and assuming that your formulation works, then down the line the focus will be shifted more to failure analysis and what it fails. And also in industry, there's a lot of depending on what you go into, but there's a lot of like failure analysis that happens when a part breaks. They don't just throw the part away and say, "Oh, the part broke." Any good engineering plan wants to understand why the part broke, such that we can stop that from happening again. So again, it kind of like when you get into material science, you can kind of pick which of those two categories you like. Do you like working on the novel design and formulation, or do you like understanding why materials fail and then coming up with ways to fix it on that end of it? So we definitely get to do both, and I think you kind of get to decide which you do more of based on what you like.
And there's a lot of industry where you're just doing a process engineer, and then after you process it and you make it, it goes to failure analysis to make sure that it works and it's suitable to be sold to the general public or whoever your audience is. Okay, just in general for MSc, what's the average workload? I assume you're talking about classes and what is it like as a student. So it depends on if you come in with a lot of credits. If you don't, typically I like to see my students around 15 credits a semester. Right, that's 15 hours of in-class work. We talked about this in the earlier session tonight. If you're going to do well in school, and Luke can attest to this, you need to spend 15 times 3 outside of class doing class-related work.
Mm-hmm.
All right, and that's equivalent to about 45 hours. So a 15-hour credit load is a full-time job for all of my students. Right, Luke?
Yes, absolutely. And one of the best things I've heard for that is when you're coming into classes, treat it like a job. Don't try and space out and just relax. It's like when you come to work, you work for a solid period of time, and then you get to go home and relax. So when you're doing your classes, treat it like that. When you come to class, focus on your classwork and do it on the front end instead of end up trying to play catch up on the back end. The other thing I would say to this is when you do research, it seems like it's a lot of extra work, but compared to classwork in your beginning couple years, it's a lot more heavy with classwork that is like sort of book studying, like doing equations, understanding the mathematics and like what is happening in this stuff. And then when you get into more like undergraduate research, it's more about like the hands-on work and actually doing things that are real instead of understanding the theory behind it. And that was one of the things that I really liked is once I got into undergraduate research, it was like, oh yeah, like this is why I wanted to become an engineer. It wasn't to like be reading equations and understanding theory all the time. It's to actually apply that to something. And so once you're able to kind of shift from the entry classes, which are making sure you understand the theory, into applying that theory, I think it becomes a lot more fun. But again, you have to have a good understanding to make that possible.
Approximately how many students are in the whole materials engineering program? Okay, here at Virginia Tech, there are 200 undergraduate students. At most, we've had 250. When I came to this department 8 years ago, there was only 120. Right? So we have grown exponentially in the past few years, and we are expected to continue to grow as we're building a new building. We're going to move into a new building next summer, and it's going to be great. We're going to have all new labs. Everything's going to be fantastic and shiny brand new. I love it. So material science engineering, we are one of the fastest growing material science departments in the country, where we have almost doubled in size. Our classes have ranged from, when I started, there was 20 in a graduating class, and now there's average about 70. At most, we had 105 in a graduating class. So again, with that many people, we work really hard to make sure the labs are small. So all of these examples that Luke gave you, he did himself. It wasn't him watching a faculty or a TA or a grad student do the work. He did the work. And it's very important to me and to everyone in this department that you guys have the hands-on experience. Luke, you want to add anything?
Yeah, just to tail off that, I definitely agree that like I was saying earlier, like understanding the theory is good, but there's nothing that compares to actually doing it yourself and having the hands-on experience. Not only do you understand how the theory applies to real life, but there's a lot of like common errors that will happen when you're working with processing materials or different types of technology. And the only way that you really get to experience and be able to like preemptively prevent those things from happening is by having experienced them yourself and knowing what to look out for. And that gives you definitely a step up when you go into industry and a real job or even academia when you're working. And if something starts to go off, instead of just being lost, like it's not working, you can be like, what are the things that I experienced that this happened before on? And if you've done hands-on work, then you have like a lot more clues to start out to come up with the answers for that of why it's not working and how you can fix it.
Okay, everybody, we're going to wrap up. I thank you for sticking with us through the difficulties with the sound and with losing power in the building. Fortunately, batteries were invented by material scientists, and we were able to proceed on. Have a good night, everyone.